Welcome to Civil Engineering Edge, where we break down complex engineering concepts into clear and powerful insights. In today's video, we're diving into the fascinating world of pavement design in civil engineering, from core principles to future-ready technologies. Whether you're a student, a professional, or just curious, this video will pave your path to knowledge. So don't forget to like, share, and subscribe for more engineering brilliance. Let's hit the road, literally. 1. Pavement design in civil engineering. Pavement design is a crucial part of transportation engineering. It involves creating a durable, cost-effective, and efficient surface for vehicles and pedestrians to travel on. The main objective of pavement design is to distribute the load from vehicles safely to the subgrade beneath, preventing structural failure and ensuring user comfort. Civil engineers must consider factors like traffic load, soil conditions, climate, and material availability when designing pavements. A well-designed pavement not only reduces maintenance costs, but also enhances road safety, fuel efficiency, and travel speed. It ensures that roads can handle heavy loads and remain functional for decades. There are two main layers in pavement design: the surface layer and the base, sub-base layers. The surface layer deals directly with the traffic load, while the base layers transfer the load to the subgrade. Each must be carefully engineered using materials like asphalt, concrete, gravel, or geosynthetics. Modern pavement design is not just about strength, it's about sustainability, longevity, and smart infrastructure. With increasing urban demands and environmental concerns, civil engineers are innovating faster than ever. And up next, we'll dive into the principles that form the foundation of this design process. 2. The principles of pavement design. Pavement design relies on key engineering principles that ensure performance, safety, and durability over time. These principles are rooted in structural mechanics, material science, and traffic analysis. The primary goal is to distribute traffic-induced stresses from vehicles evenly through the pavement layers to the subgrade. The California Bearing Ratio (CEB) method and mechanistic empirical design are commonly used to calculate pavement thickness based on anticipated load repetitions and soil strength. Traffic load estimation is essential. Engineers predict the type and number of vehicles expected over the pavement's life, converting them into equivalent single-axle loads (ESAALs) for analysis. Pavements must be designed to endure this loading without excessive deformation, cracking, or rutting. Another principle is material selection and layer configuration. Surface layers must resist abrasion and weather, while base and sub-base layers provide load-bearing support. Drainage design is also vital. Water weakens subgrade soils and accelerates pavement failure, so proper water management must be integrated. Temperature effects, such as thermal expansion and contraction in rigid pavements, are also considered, especially in regions with extreme climates. By applying these principles, civil engineers ensure that pavements meet functional performance, safety, and cost efficiency standards. In the next section, let's explore the different types of pavements and how each one serves a unique purpose. 3. Types of pavements and their description. Pavements are broadly classified into three main types: flexible pavement, rigid pavement, and composite pavement. Each has distinct characteristics, construction methods, and use cases. 1. Flexible pavement. This is the most common type, made of multiple layers with the top surface typically composed of bituminous materials, asphalt. These pavements flex under load, hence the name. They transfer stress from vehicles gradually to the subgrade through various layers: surface, binder, base, and subbase. Advantages: lower initial cost, ease of repair. Common uses: highways, city roads, and rural roads. 2. Rigid pavement. Rigid pavements use cement concrete slabs that have high bending strength. Unlike flexible pavements, they distribute loads over a wider area due to their rigidity. Advantages: long lifespan, 30+ years, low maintenance. Drawbacks: high initial cost, complex construction. Common uses: airports, expressways, and urban intersections. 3. Composite pavement. These pavements combine both flexible and rigid layers, for example, a concrete base with an asphalt surface. Advantages: improved durability, noise reduction, better performance in mixed traffic conditions. Use cases: heavily trafficked areas requiring structural strength and surface flexibility. Each pavement type is chosen based on traffic volume, climate, soil conditions, and budget. For instance, flexible pavements are favored in regions where quick repair and lower costs are needed, while rigid pavements suit places with heavy loads and long-term service demands. As infrastructure demands evolve, engineers are turning to futuristic solutions. Let's now look at how technology is reshaping pavement design for the future. 4. Futuristic pavement with modern tools. The future of pavement design is intelligent, sustainable, and adaptive. Civil engineers are now integrating advanced tools and materials to create pavements that are not only strong and long-lasting, but also smart and environmentally friendly. 1. Smart pavements. Modern roads are being embedded with sensors and IoT devices that monitor temperature, load, cracks, and moisture. These smart systems provide real-time data, enabling predictive maintenance and reducing sudden failures. For example, roads in the US and Europe are using fiber optic sensors to monitor stress levels and notify maintenance teams before damage becomes severe. 2. Self-healing materials. Self-healing asphalt and concrete use embedded capsules of healing agents like bitumen or bacteria-based compounds. When a crack forms, these agents are released, automatically sealing the gap. This technology significantly extends pavement life and reduces repair costs. 3. Permeable pavements. To address urban flooding, engineers are developing porous pavements that allow rainwater to seep through the surface and recharge groundwater. These pavements reduce runoff, minimize erosion, and improve sustainability in cities. 4. Recycled and green materials. Eco-friendly pavements are on the rise. Using recycled plastic, rubber, fly ash, or waste glass, these materials reduce carbon footprints and promote a circular economy. Additionally, cold mix asphalt reduces the need for heating, saving energy during construction. 5. Advanced design software and AI. With tools like HDM4, AutoCAD Civil 3D, and AI-powered simulations, engineers can now design pavements with more precision. These tools allow for performance-based analysis, real-time modifications, and cost optimization throughout the life cycle of the road. 6. Solar roadways. An exciting innovation is the integration of solar panels into pavements to generate electricity. Though in the experimental phase, projects in France and China have demonstrated its potential to power street lights and nearby buildings. As cities grow smarter, pavements must follow suit. These futuristic solutions promise not only longer-lasting roads, but also greener, more connected infrastructure, laying the groundwork for sustainable urban mobility. And that wraps up our journey through pavement design in civil engineering, from its basic principles to cutting-edge innovations. If you found this video helpful, hit that like button, subscribe to Civil Engineering Edge, and tap the bell icon so you never miss an update. Got questions or ideas for future topics? Drop them in the comments below. Until next time, build smart, stay strong.